All right, yes, prep. Let's get this next video started. This is actually a reshoot of the first video I ever recorded last year with Mr. Brandenburg. I noticed there have just been a couple of changes in the course since then that I wanted to include in this video. So let's get started. Since this is an AP review video, there are going to be a lot of big ideas that manifest themselves into the video. But our focus topic is functional analysis. And by functional analysis, what I mean is problems that normally you'll be given a graph of a function or maybe its derivative, and then you're going to be asked questions about absolute maxima, points of inflection, concavity, a lot of writing involved in problems like this, and also just a lot of memorization of some formulas and definitions. It's not so much formulas, but more definitions and big ideas. So what I'm doing in this first slide is just a summary of things that I would expect you to know and to know cold. I want to emphasize that again. All of the things listed on these first three slides have to be just internalized. They're at the point where you memorize them, you don't even doubt them. So when it comes to the first derivative, what we know is if f prime is positive, then the original function is increasing. Furthermore, if the original function is increasing, then the derivative must be greater than 0. That also means that when the derivative is negative, the function is decreasing. And when the function is decreasing, the derivative is negative. These four, I would say, for the most part, all of my students know them. They know them well. It's when we start to dig a little bit deeper where things don't go as well as I would like. So let's start with relative maximum. If your graph has a relative maximum, then we're looking at this. However, we could also be looking at this situation. At both of these points, these are relative maximums. To say that the derivative is equal to 0 is true in the first example, but it's false in the second example because we have a cusp point. So to just say a relative maximum is where the derivative is equal to 0 is not enough. That's not sufficient, and it's generally just flat out wrong because that only describes some of the situations for a max. Now, what is true all of the time is that if your function has a max, this kind or that kind, then the graph is increasing before the point, decreasing after the point. That's true in both cases. Further, you could say that the derivative, f prime, is greater than 0 before the max, and f prime is less than 0 after the max. Those are the things that are true. These are the things that you can use to verify a function has a relative maximum. If you say the derivative is 0, it's wrong. So let's stop saying that. Okay. So then, obviously, when it comes to a relative minimum, we're looking at a graph that looks like that, or possibility a graph that looks like that. What's true with both graphs? The function is decreasing, then it is increasing. Where we change from decreasing to increasing is the relative minimum. You could also phrase it as the derivative is negative, and then the derivative is positive. Both of those statements are true when it comes to relative minima. We're going to stop saying the derivative is equal to 0. Last point, when we talk about a function having a critical point, critical points come in, I like to describe them as two flavors. A critical point is where the derivative is equal to 0, or, big or here, where the derivative does not exist. If the derivative doesn't exist, then the function is not differentiable at C. So that's the summary of all of our first derivative information. This must be at the point of mastery before you walk into the exam. See tons of questions on the multiple choice as well as the free response that involve first derivative information as well as second derivative information. By second derivative, I mean the derivative of the derivative. So when the second derivative is positive, we refer to that as concave up. So if I tell you the second derivative is positive, then you know the function is concave up on that interval. Also, if I tell you that the function is concave up, then that does imply that the second derivative is positive. If the second derivative is negative, then the function is concave down. And if the function is concave down, the second derivative is negative. Should have drawn this earlier, but by concave up, that's the example I tend to think of for concave up. I think of it as a cup that would hold water. Because the second derivative is positive, I sometimes write two little plus signs to remind myself concave up, cup that holds water, second derivative is positive. Looks like a happy face. Concave down looks something like that. Second derivative is negative, kind of looks like a sad face to me. And it would be sad if we don't have under control our first and second derivative information. The graph has a point of inflection. A point of inflection is where f double prime changes sign. Again, I did not say it's where the second derivative is 0. If the graph has a point of inflection, then the second derivative changes sign. Normally, if you have the graph in front of you, you might see, okay, here's concave up, then the graph becomes concave down. It's over here at this point where we switch from concave up to concave down. That's our point of inflection, which I'm going to abbreviate as POI. Lastly, if the second derivative is equal to 0, or if for some reason the second derivative is undefined, these are possible inflection points. Emphasis on possible. Not a guarantee, because the only guarantee of an inflection point is that the sign of the second derivative changes. That is a change from positive to negative, or from negative to positive. They're going to set you guys up for failure. There's going to be some questions about the second derivative equal to 0. Is that a point of inflection? No, not good enough. We're looking for a change. Okay. And then lastly, this is the summary table that has to just be under control. It didn't actually show up that well in the slide. Let's see if I can make this better. This top row is information about f of x. The next row is information about the derivative, that's f prime, followed by f double prime. Okay, the heading over here is increasing. If you know your function is increasing, then we know the derivative is greater than or equal to 0. And we know no information about the second derivative. If your function is, if the original function is decreasing, then the derivative will be less than or equal to 0, and we have no information about the second derivative. If you have a relative max, that's what that says up here, then what we know is that the derivative changes from positive to negative. Usually I abbreviate it as change from positive to negative, and that change, that triangle, the delta, is legitimate notation on the AP exam. So let's go further. If we have a relative minimum, well, if you have a relative minimum, then the sign of the first derivative changes from negative to positive. We'd write that as change from negative to positive. Critical points, that's where the first derivative is equal to 0 or undefined. If you have a cusp point, our favorite word, that means you have a sharp point in the graph. Looks something like that. Or, let me make it bigger. Or it looks like that. These are cusp points. These are sharp turns. The derivative does not exist. The derivative is undefined. If your function is concave up, well, we already said earlier that the second derivative is positive. But if the second derivative is positive, then the first derivative is increasing. Furthermore, if the function is concave down, then the second derivative is negative. And that means that the graph of the first derivative is decreasing. Now, one thing to note when it comes to describing intervals where a function is increasing or decreasing, we tend to use brackets. That's for increasing and decreasing as long as the function is defined at the endpoints. However, when it comes to concavity, when we describe intervals where a function is concave up or concave down, we go with parentheses. Do not use the brackets when it comes to concavity. You are very likely going to lose the point, and that would be sad. If you have a point of inflection, then what do we know? If you have a point of inflection, then the second derivative changes from positive to negative, or negative to positive. But if the second derivative is changing sign, then what happens at the first derivative level is your first derivative changes from increasing to decreasing, or decreasing to increasing. Okay, those first couple of rows, you want to make sure that you can fill in every single one of these without even hesitating. Okay, this last row is only going to be used for the example of concave up or concave down. And this is a problem that I'm still seeing with my AP Calculus kids. Often you will be asked if an approximation is an overestimate or an underestimate. You might even be asked to decide if the tangent lines are above the graph or below the graph. Let's look at this one. If I have a function that's concave up, let me draw a tangent line. That tangent line lies below the curve. So does that tangent line. So does this one. Every tangent line that you would draw to a graph that is concave up, those tangent lines will be below the curve. Therefore, the estimates that you're going to get from a function that's concave up, if you're using a tangent line approximation, these are all underestimates. They have to be. They have to lie below the curve if the function is concave up. If your function is concave down graphs look like that. You pick a different color. Every tangent line that you draw is going to be above. I can see that. They're all above. Since the tangent lines are above, what we have is we have an overestimate. Okay. So that's it for the summary table. At this point, what I've done is I've picked 3 free response questions, all of which have appeared on past AP exams. And I want to take all of this information and show you how it's likely to appear on either the multiple choice part of the exam or on the free response. Expect to do a lot of writing. Okay, this first question showed up on the 2008 exam, 2008 Form B. Form B is the exam that you take if you are not present the day of the AP exam. If you are on homebound services, you're absent, whatever the reason might be, this is the exam you would take. So we have a graph. G is a continuous function. This is important information. I'd want to box that off. G is continuous. Good. Furthermore, we know that G of 2 is equal to 5. That means I have the point 2, 5 is on the graph of G. The graph of the piecewise linear function G prime. This graph up here is the graph of G prime. They're going to constantly expose you to questions like this. The derivative of G, shown on the interval -3 to 7. Because I'm only interested in the interval -3 to 7, I like to think of this as putting blinders on. I can't make any conclusions about what happens outside of this interval. All of my answers need to be confined from -3 to 7. And we're just going to be really careful. Do not make statements outside of this interval. In part A, we're asked to find the x-coordinate for all points of inflection of the graph of y equals g of x on that interval. Part B, we want to find the absolute maximum value of g on that closed interval. Absolute maximum, that's going to take some work. C, we want to find the average rate of change on the interval -3 to 7. And D, we want to find the average rate of change of g prime on that same interval. And then we need to actually answer the question, does the mean value theorem applied on that interval guarantee a value of C such that g double prime is equal to this average rate of change? Why or why not? So let's start with part A. I'm going to keep the graph for all of the slides, but I wanted to give myself some room to work. So, Find the x-coordinates for points of inflection. And what I'm about to do now is what I really do when I see questions like this. If G has a point of inflection, G double prime changes sign. Well, if G double prime changes sign, G prime has to change from increasing to decreasing, or from decreasing to increasing. I want to connect everything back to G prime. G has a point of inflection, therefore the second derivative changes sign. If the second derivative changes sign, then G prime changes from increasing to decreasing, or decreasing to increasing. Well, let's examine the graph. Starting at -3, continuing all the way to -1, G prime is increasing. From -1 to 1, I am still increasing. No change yet. However, at x equals 1, I am changing. My graph is increasing before 1, decreasing after 1. That means x equals 1 is a POI, point of inflection of G, because G prime changes from increasing to decreasing. Great. Let's see if that happens anywhere else. After 1, we're decreasing until 4. After 4, we're increasing. Hey, that means x equals 4 is a point of inflection of G, because G prime changes from decreasing to increasing. And what I'm writing for all of these problems, this is absolutely 100% what I would be writing the day of the AP exam. I'm not going to abbreviate any more than I've done already. Abbreviations like DEC for decreasing, that's fine. INC for increasing. The little delta for the change. B/C for because. POI, point of inflection. These are things that are acceptable. I would not want to test out new notation and new shortcuts the day of your AP exam. All right, part B. Find the absolute maximum value of G on that interval. Absolute maximum. If you are at Southwest or East End, if you are my student, we have a process that we go through when we look for absolute extrema. First, we look for a candidate. Where might G have a max? Well, G has a max when G prime changes from positive to negative. Well, let's look at the graph. Where does G prime change from positive to negative? Another way to say that, where does G prime switch from above the x-axis to below the x-axis? That happens right over here at x equals 2. Although x equals -1 is a root, we're changing from negative to positive, so that's not a max. X equals 6 is also a root, we're changing from negative to positive, so that's not a candidate for a max. Our only candidate is at x equals 2. Next, we evaluate our candidates. Another way to say that, we're going to plug 2 into the graph into the function G, because we want the absolute maximum of G. I find G of 2 to be 5. They told us that in the beginning. Now we're not done. Next, we need to evaluate the endpoints. And this is where we have some work to do. The endpoints of the interval are at -3, so I need to find G of -3, and 7. I need G of 7. Well, all I know is that G of 2 is equal to 5, and I have information about the derivative. How am I going to find G of -3? That's my fundamental theorem of calculus, which I'll write up here. The fundamental theorem of calculus, which you just need to know, is that for a function, f, the value of the function at the end of an interval is equal to the value of the function at the start of an interval, plus the total change of the function over the interval. So I'm going to write that as f of b equals f of a plus the integral from a to b of f prime of x dx. That's your fundamental theorem of calculus. We use that all the time. Well, let's apply it to g of 7. Even though I wrote g of negative 3 first, let's write g of 7. G of 7, the value of the function at 7 is equal to the value of the function at 2 plus how the function changed, that's g prime, from 2 to 7. In order to determine this, I need to figure out, let's see, definite integral from 2 to 7 of g prime. That means how much area is there from x equals 2 to x equals 7. What's the accumulated change? Well, if I break this up, I can see that from 2 to 6, there's 6. From 2 to 6, we have a triangle lying below the x-axis. This length here is 4. The height of this triangle is 2. Take the base times the height, that's 8. Cut it in half, that's 4. Because we're below the x-axis, we're going to make that negative 4. Area of this triangle over here, you have a base of 1, a height of 1. Cut that in half, 1/2. We're above the x-axis, that's positive. So we have g of 2 is 5 plus the definite integral here. That means we're going to add negative 4. We're going to add 1/2. 5 plus negative 4 is 1 plus 1/2 is 1.5, or I'm going to write 3/2. 1.5, doesn't matter. Now g of negative 3, let's use that fundamental theorem again. It's g of 2 plus the integral from 2 to negative 3, g prime of x dx. Because you're finding the area from 2 to negative 3, from 2 all the way out to negative 3, that integral is written in sort of the wrong order. We don't like to have the lower limit of integration. I'm sorry. We want the lower limit of integration to be the smaller number. That's not the case here. So we are allowed to switch the order. However, I always call it the transactional cost. You can switch it, but it costs you something, and that cost is that now the integral, the answer, we're going to have to take the opposite sign. So if I'm going to find the area from negative 3 to positive 2, we have a triangle below the x-axis. That's 2, that's 4, that's 2 times 4 is 8. Cut it in half, we have negative 4. This triangle, 3 is the base, 1 is the height. Cut that in half, you're going to get 3/2. So g of negative 3, a little bit of bad planning on my part. G of negative 3, 5 minus the total area from negative 3 to 2. That's negative 4 plus 3/2. We get 5. If I distribute the negative, I get plus 4 minus 3/2. 5 plus 4 is 9 minus 3/2 is 15 over 2. As a decimal, that's 7.5. Now, before you're like, oh my God, this is the longest problem ever, we have to actually answer their question. So step 4 is always your conclusion. Step 1 was identify your candidate. Step 2, evaluate your candidate. Step 3, evaluate the endpoints. Step 4, draw your conclusion. The question was, find the absolute maximum value of g on that interval. Justify your answer. Well, all of this is the justification. We have to make a decision. Is the maximum value at the candidate that has a value of 5? Is the maximum value at 7? That value is 3/2 or 1.5. Or is the maximum value at negative 3, 7.5? Ding, 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 ding. The conclusion would be the absolute max value of g on the interval, we want to be really careful, is 7.5. The question didn't ask anything about where does it occur, simply what is the maximum value. This is your final answer. I know most of my students have gotten very good at this process. This is a non-negotiable. We're going to follow these 4 steps all the time, and it's going to get you to get all the points possible. All right, part C. Find the average rate of change of g on the interval negative 3 to 7. Average rate of change. I know that by another name. Average rate of change is the slope. The way we found slope, change in y over the change in x. For this problem specifically, I want the average rate of g, so that's my function, over the interval -3 to 7. A is going to be -3, B is going to be 7, so the average rate of change will be g of 7 minus g of -3 over 7 minus -3. G of 7, we already determined in part B, is 3/2 minus g of -3, we found that to be 15 over 2. And we're going to divide it by 7 minus -3. If this question appears on the free response part of the test, my students have been well trained to stop because you're going to be throwing points away. But let's go a little bit further. 3/2 minus 15 over 2 is -12/2. 7 minus a -3 is the same as 7 plus 3. That's 10. -12 over 2 is -6. -6 divided by 10 reduces to -3/5. Although it is easy and quick to get to -3/5, think about the 20 seconds that you spent going from this perfectly acceptable answer over to this one. Look at all the places you could have made a silly yet lethal sign error, fraction error, reduction error. When you had the point over here, you could lose the point going over to here. And it's time that you don't have to waste. So let's do that. All right, last one for this question. Oh, and if I didn't say at the beginning of the problem, this is a calculator inactive question. Clearly, I've not been using my calculator for any of these questions so far. Part D, find the average rate of change of, again, average rate of change. If I knew it in Part C, I can do it again here in Part D. But now it's of G prime on the same interval. Then, does the mean value theorem applied on this interval guarantee a value of C for -3 less than 3 less than 7, such that G double prime is equal to this average rate of change? Well, let's start with what I know. I need average rate of change of G prime. Well, that's G prime of 7 minus G prime of -3 over 7 minus a -3. Now, G prime of 7, where's that going to come from? This represents the graph of G prime. What I'm asking for is, what is the value of G prime when x is equal to 7? Well, I can see from the graph, that's 1. Minus G prime of -3. What's the value of G prime when x is equal to -3? I go to my graph. That's -4. And then in the bottom, 7 minus a -3. 1 plus 4, I get 5. 7 plus 3 is 10. That's a half. Done. I've answered the first part of the question. Now, let's see. The mean value theorem, that's another one that needs to just be under control. Mean value theorem looks something like this. If f is continuous and differentiable, so it has to be continuous on the closed interval, differentiable on the open interval. If f satisfies both of those, then there exists a c in the interval AB such that f prime of c, that's the derivative, that's the slope of the tangent line at c, is equal to f of b minus f of a over b minus a. I didn't do a good job with my paper usage here. So one more time, mean value theorem. If you have a function that is continuous on a closed interval, differentiable on an open interval, then there has to be a value of c inside of that interval such that the derivative of the function, the slope of the tangent line, is equal to the slope of the secant line, f of b minus f of a over b minus a. So let's go to the question. What we found average rate of change of G prime. g prime of 7 minus g of negative 3 over 7 minus negative 3. Does the mean value theorem applied on that interval guarantee a value of c such that g double prime is equal to this average rate of change? Well, let's think about this. In order to use the mean value theorem, is g prime continuous? Yes, I can see from my graph that g prime is continuous. There's no holes, there's no jumps, there's no breaks, there's no vertical asymptotes. Is g prime differentiable? Is it smooth? Are there any vertical tangents? Well, right here at -1, I have a sharp turn. I have a different slope coming into that point than I do leaving that point. So my function fails to be differentiable at -1. It fails to be differentiable at 1 and at 4. G prime is not differentiable. So what that means is that the mean value theorem does not apply. Therefore, 3 dots, there is no guarantee of a c, of a value of c, in this interval -3 less than c less than 7, such that g double prime of c is equal to 1/2. Now, maybe there is some point, but there's no guarantee. The mean value theorem, we like to call it an existence theorem. The mean value theorem promises you will find such a value of c that satisfies this relationship up here, but only if the function is continuous on the closed interval and differentiable on the open interval. So that's it. That concludes our first free response question. And if you're at Southwest or East End, we actually worked through that problem in a journal entry earlier this week. Now, I had hoped that we would have time to do these 2 questions this week as a journal, but we didn't get to, so I'm doing them in the video. This next question appeared on the 2004 AP exam. It's question number 5. Question number 5 is always calculator inactive. We have a graph, and let's see. The graph of the function f, shown above, consists of a semicircle, good, and 3 line segments. Let g be this function over here, g of x equals the integral from -3 to x f of t dt. We want to find the value of g of 0 and then g prime of 0. That's part A. In part B, we want to find all values of x in that open interval where g attains a relative maximum. C, we're going to want to find the absolute maximum value of g on a closed interval. We just went over that process in the last one. And then D, we want to find all values of x in the open interval at which the graph of g is the point of inflection. This one has a lot of similarities to the last question. It's certainly not identical. So let's get going. All right, and I want to make sure I don't blow it here, because I did not include this information on the second slide. G is the integral of f of t dt from -3 to x. So the first one, find g of 0. Well, how do I find g of 0? If this is the definition of g, then I'm going to evaluate that function at 0. Well, how am I going to do that? I need to find the area, or the accumulation, from -3 to 0. So starting over here, going to 0, what's that area? If you want to break it into a triangle and a rectangle, that's fine. I'm going to go with the trapezoid method. Area of a trapezoid, 1/2. Base 1, base 2 times the height. My bases are perpendicular, so that has a height of 2. That has a height of 1. The height, that's this guy here running perpendicular to the bases. My height is 3. Base 1 plus base 2, that's going to be 3 times your height, which is 9. Cut that in half, we're going to get 9/2. So g of 0 is going to be 9/2, or if you prefer, 4.5. G g prime of 0? Well, in order to do that, that means I'm supposed to take the derivative of g and then evaluate that at 0. Well, let's see. I want to take the derivative of the function, which is an integral from -3 to x of f of t dt, and then I want to evaluate that at 0. And I'm trying to be very, very specific with my notation. Okay? You might recall, I hope that you do, that when you take the derivative of an integral of a function where you start at a constant and you end at the variable, all of this, thank you, second fundamental theorem of calculus, becomes just the function evaluated at that upper endpoint. The derivative of the integral of a function from a constant to a variable is just going to be the original function evaluated at x. And then we plug in 0. So we get f of 0. Well, what's the value of f of 0? Where on earth does that come from? That comes from looking at our graph. This is the graph of f. F of 0 is 1. That's it. Done. That was part A. Kind of snuck in that this guy over here to go from this step to this one is your second fundamental theorem in calculus, which I'm just going to abbreviate as FTC. If you're not familiar with the second fundamental theorem in calculus, look it up. All right, let's look at part B. Find all values in which g attains a relative maximum. All right, a relative maximum. What do I know? If g has a relative max, then that means g prime changes from positive to negative. Well, what have we already figured out? We know that g is the integral from -3 to x f of t dt, and we know that g prime is that derivative. And so when I take the derivative of that integral, I just get f of x. So from now on, when we're being asked questions about g prime, that is equivalent to asking the same question of f of x. G prime is equal to f of x. So let's see, if g has a max, then g prime changes from positive to negative. Well, what that really means is that f must be changing from positive to negative. If I've got the graph of f here in front of me, this should be an easy question. Where does f change from positive to negative? Well, right here at this point at x equals 3. That's it. But that's the logic, that's the evidence you need to provide in order to get to this point. Let's move on to part C. Find the absolute maximum value of g on that closed interval. And again, I want to make sure I've got the right function. G is your integral from -3 to x of f of t dt. Absolute maximum. Let's go through that process. Step 1. Candidate. Where might I have an absolute maximum? I think we already did that in part B. And we said that was going to happen at x equals 3. 2. Evaluate the candidate. Let's actually find g of 3. G of 3 is the integral from -3 to 3 of f of t dt. Here's x equals -3. Here's x equals positive 3. I need the accumulated change going from -3 to positive 3. Easy parts. We already know that that's 9/2. So we're starting at 9/2 plus. Now here's where we need to get a little bit tricky. I need to find, we've already found this area here. That's what I just shaded in light blue. I'm going to zoom in a little bit. Maybe this will help. I need to find how much area there is here, and this last part is a triangle. That should be the easy part. But to draw your attention to the part of the graph from 0 to 2, that's going to require a little bit of trickery. This part that I've shaded in the light blue Although they might look like triangles, they are not triangles. All I can tell you is that these are shapes that lie below the semicircle. Now, with a little bit of geometry maneuvering, you might recall, well, let's see, the area of a semicircle, okay, now that I'm zoomed in, I'm all kind of messed up. The area of a semicircle is pi r squared divided by 2. Let's see, the semicircle starts, the diameter goes from 0, 1 to 2, 1. So the diameter is 2, the radius is 1. So the area of my semicircle is pi times 1 squared over 2, which is pi over 2. That represents the area inside the semicircle. I need the area underneath the semicircle. Well, how could we do this? I could see this as a rectangle. That rectangle is 2 spaces wide, it's 1 space tall, so that has a total area of 2. I'm going to subtract off the pi over 2. So let me go back to my integral over here. We said we had 9/2 plus 2 minus pi over 2. That accounts for these 2 little pieces. And then we need to add on to that this little triangle over here that has a height of 1 and a base of 1. 1 times 1, cut that in half. So we have 1/2. Wow. Okay. That just took some work. We might want to simplify it. Maybe, maybe not. We'll come back and decide that later. 3, what do we need to do? We need to evaluate the endpoints. More work to do here. I'm going to evaluate the endpoints. I'm looking from -5 to 4. I'm going to need to find g of -5. I'm going to need to find g of 4. G of -5 is the integral from -3 to -5, f of t dt. We mentioned this in the last problem. Your lower limit should be smaller than your upper limit. That's not the case here. So we switch it, and that transactional cost is we throw in a negative, and then it's f of t dt. What's the total area from -5 to x equals -3? I can see by inspection that these are equal but opposite in area, so that has a value of 0. Good. To find g of 4, I need the area from -3 to 4, f of t dt. So I'm starting over here at -3. I'm going all the way to +4. So let's not recreate the wheel. Let's use the information we know. This first part is 9/2. These 2 little pieces down here is 2 minus pi over 2. We then added on 1/2, but I have to take into account this little piece down here that has an area of -1/2. Those are going to cancel. So the question was, find the absolute maximum value on the closed interval -5 to 4. My choices are 9/2 plus 2 minus pi over 2 plus 1/2. That's one option. My second choice is 0, and my third choice is 9/2 plus 2 minus pi over 2. Which of those appears to be the largest? You have no access to a calculator. Let's see, 9/2 is 4.5, plus 2 is 6.5, minus, well, I know pi is between 3 and 4. If I take that divided by 2, that's some number between 1.5 and 2. 4.5 plus 2 is 6.5, minus, at most, 2, plus 1/2, compared to 0. 0 is smaller. 9/2 plus 2 minus pi over 2, but then don't add on anything else. Your conclusion should be G has an absolute maximum value of, what was it? 9/2 plus 2 minus pi over 2 plus 1/2 on the interval -5 to 4. Spending time to reduce this answer, get a common denominator, is generally time wasted, time thrown away that you don't have. So please don't do that. All right, part D. This is the last one for this question. Find all values of x in the open interval at which graph of g has a point of inflection. What do we know? We know if g has a POI, then g double prime changes sign. That could be a change from positive to negative or negative to positive. Furthermore, we know, we've seen already that g is this function. We know that g prime is equal to f of x. If g prime is equal to f of x, and we want to have conversation about g double prime, well, take another derivative. If I take another derivative on the left, I get g double prime. If I take another derivative of f, I get f prime. Where, if g double prime changes sign, and g double prime and f prime are the same, then where does f prime change sign? If you don't like answering that question, you could go further and say, oh, that means that f changes from increasing to decreasing, or decreasing to increasing. Let's look at the graph. Where does f change from increasing to decreasing? From -5 to -3, the graph is increasing, and then it's decreasing. So we have a change at x equals -3. From -3 to 0, the graph is decreasing. From 0 to 1, still decreasing, not a change. At 1, we change to increasing. So there we go again, x equals 1. Now, let's be careful. At x equals 2, yes, that is a sharp point. But all I'm asking is, does the graph change from increasing to decreasing? Yes. There are 3 points of inflection. X equals -3, x equals 1, and x equals 2. And that, my friends, is the conclusion of this problem. Let's do one more. All right, new question. This was on the 2009 AP exam, Form B. Again, the question that you had to answer if you didn't take the test the day everybody else did. This is question 3, and on the 2009 exam, you could still use a calculator on question number 3. It was starting last year, the 2011 exam, that you could no longer use your calculator. So, we have a continuous function f. Good. I always like to box that information. Draw attention to it. F is continuous. Good. Closed interval. We know that means don't look outside the interval. The graph of f consists of a line segment and a curve, not a semicircle, just a curve that is tangent to the x-axis at x equals 3. We'll come back and talk about that in a moment. As shown in the figure above, on the interval 0 to 6, the function is twice differentiable. Twice differentiable means f prime exists and f double prime exists. Both of those exist. Both of those exist, f prime and f double prime. Furthermore, f double prime is greater than 0. That means that the graph is concave up. The graph of f is concave up. I can see that. So let's go through this one more time. The graph of f is continuous. No holes, no jumps, no breaks, no vertical asymptotes. I can see that. F is defined on that closed interval, but don't look outside. Nothing over here. Nothing over here. The graph consists of a line segment and a curve tangent to the x-axis. 2 things you were just told. The graph is touching x equals 3 at the x-axis. So that means that the graph passes through the point 3, 0. X equals 3 is our root. The other thing, if it is tangent to the x-axis, it's touching and has the same slope. Therefore, f prime of 3 is equal to 0. Those are the 2 bits of information. And on the interval 0 to 6, so just from 0 to 6, f prime exists and f double prime exists and the function is concave up. Okay, that was a packed question. Now we need to, oh, that wasn't even a question. That was a packed introduction to the problem. Part A, is f differentiable at x equals 0? Use the definition with one-sided limits to justify your answer. Part B, for how many values of a is the average rate of change of f equal to 0? We have to give a reason. Part C, is there a value of a with -4 less than or equal to a less than 6, for which the mean value theorem applied to that interval guarantees a value of c such that a is less than c is less than 6, at which f prime of c is a third? We're going to justify our answer. D, the function g defined by the integral of f of t from 0 to x for the interval -4 to 6. On what intervals contained in -4, 6 is the graph concave up? And explain your reasoning. And we need to be able to do this in 15 minutes. So, ready, set, here we go. I'm going to keep my marked up version of the graph close. A, is f differentiable at x equals 0? Well, let's answer that. No, it's not differentiable at x equals 0. Now, here's the mistake. If you say no because there is a sharp point, that's true. That is true. There's nothing wrong with what's been written here. You would get 1 point for answering the question correctly. No, the function's not differentiable. The mistake is you didn't actually finish reading their question. Use the definition of the derivative with one-sided limits to justify your answer. The definition of the derivative, that was a long time ago. F prime of a is the limit as x approaches a, f of x minus f of a over x minus a. I think a lot of my students, as hard working as they are, would be caught with their pants down on this question because we've not looked at something like this in a long time. This is definition of the derivative. Okay, so where am I interested in? I'm interested in f prime of 0. So f prime of 0, what happens if I take the limit as x approaches 0 from the left? Well, let's see, we've got f of x minus f of 0 over x minus 0, which is just x. If I'm approaching 0 from the left, say this point over here, and I get closer, and I get closer, and I get closer. Now I could find the slope, I mean that's just a line. What I know is those values are all positive. The limit as x approaches 0 will be some positive number. However, if I take the limit as x approaches 0 from the right, again using my difference quotient, if I approach 0 from the right here, then closer, then closer, then closer, then closer, the slopes are all less than 0. I cannot have equality when one limit is positive and one limit is negative. Because these are not equal to each other, the limit on the left and the limit on the right are not equal to each other, this implies the limit as x approaches 0 of f of x minus f of 0 over x does not exist. Therefore, f is not differentiable at x equals 0. Okay? I think this would be as close to the ideal presentation as I would want you to get, or that I would expect you to get. Let's be careful with the notation. Let's be careful with the shorthand. One-sided limits. In order for a limit to exist, the limit from the left and the limit from the right would have to be equal to each other. Since one is positive, one is negative, they will not be equal to each other. Therefore, the limit does not exist. All right, part B. For how many values of a in this interval, -4 to 6, is the average rate of change of f equal to 0? Average rate of change of f. We're going to find f of 6 minus f of a over 6 minus a. and we need that to be equal to 0. How many times is this true? Well, what does it take for this expression on the left to be equal to 0? I know that if a fraction is equal to 0, then the numerator is equal to 0. That gets me f of 6 minus f of a is equal to 0. But if these two, when you subtract them, are equal to 0, that means that f of 6 is equal to f of a. The original question was, how many values of a? Not what values of a, how many? How many times will the average rate of change be equal to 0? That's the same as asking, how many times will the numerator be equal to 0? That's the same as asking, how many times will f of a be equal to f of 6? How many times will f of a be equal to 1? Going from -4 to 6. If I imagine a horizontal line over here at y equals 1, how many times is the graph equal to 1? One time over here, somewhere, I don't even care where, somewhere over here. So I would say this happens for 2 values of a on the interval in question, which is -4, less than or equal to a, strictly less than 6. And that's it. That's all they wanted in part B. Part C. Is there a value of a? Is there one? On that interval for which the mean value theorem applied to the interval a, 6 guarantees a value of c with a less than c less than 6, and which f prime of c is equal to 1/3. Justify your answer. This one is tricky. I will be honest and out myself here. I got this question wrong when I did it at first, because I quickly said, aha, the mean value theorem. If you want the mean value theorem, f has to be continuous. Got it. F has to be differentiable. Aha, the function is not differentiable. True, the function is not differentiable because at x equals 0 we have a sharp point. However, after careful examination of the question, they're saying, is there some value of a where a is between -4 and 6, for which the mean value theorem applied on that interval from some number to 6 guarantees that value of a? I get to pick the start of the interval that I look at, but I have to end at 6. So here's the vertical line, x equals 6. Where can I even start the conversation? Well, can a be -4? No, the function's not differentiable between those two. But I can move the one on the left, so let's move it closer. Let's move it closer. I have to look somewhere so that I am past that, past the sharp point. Is there anywhere in this interval that the tangent line is going to have a slope of 1/3? That's really what I'm asking. So I'm only looking between 0 and 6. So let's see, if I'm going to have a slope of 1/3, so is there a value of a such that that's true? Well, what I know is on the interval 0, 6, the mean value theorem does apply. Therefore, yes. Wait, let me take that back. What I know is on the interval 0 to 6, the mean value theorem applies. Done. That's what I know. Now, specifically, what I need is for f of b minus f of a over b minus a to be equal to f prime of c, which is 1/3. And they've told me that my b value is 6, so we need f of 6, which is 1, minus f of a over 6 minus a to be equal to 1/3. I'm looking for a value of a that when I use it in this expression, I'm going to get positive 1/3. And I started over here at x equals 3. if x equals 3, if this is the interval that I look at, if the slope starting from a equals 3 to b equals 6, if the slope of that line segment is 1/3, then I'm guaranteed a value of c. So let's see, if a is equal to 3, f of a is equal to 0. 1 minus 0 over 6 minus 3 is 1/3, check. Therefore, if a is equal to 3, then by the MVT, there exists a c in the interval 3 less than c less than 6, such that f prime of c is 1/3. That, oh, sorry. So I'll state the conclusion because you couldn't see it. So if I select my a value to be 3, that's where I start the interval, then by the mean value theorem, there is a value of c such that c is greater than 3 and less than 6, such that f prime of c is equal to 1/3. The answer to the question is yes, there is a point, and this is the point that you'd have to select. All right, last one, and then the bell's going to ring. Part D, the function g is defined by g as the definite integral from 0 to x for the interval -4 less than x less than or equal to 6. On what intervals contained in -4, 6 is the graph of g concave up? G is the integral from 0 to 6 f of t dt. G concave up, g double prime is greater than 0. I have a function over here defined by an integral. I want to get to the second derivative, so I take the first derivative. We saw this in the last problem. The derivative of the integral of a function starting at a constant, ending at a variable, is simply f of x. I need to get to g double prime, so I take another derivative, and I get f prime. Where is f prime greater than 0? Well, if f prime is greater than 0, then what does that mean about f? I have a graph of f in front of me. I have to answer the question about f increasing. Where is f increasing? I can see from my graph that f starts to increase at -4, continues to increase until I hit 0, and that the graph starts to increase again at 3 and ends at 6. Now, if this is what I leave as my answer, I am so close, but I think the AP folks would not award you the full points because it is true that f is increasing on this interval. But if I'm strictly looking at where f prime is greater than 0, which I am because we need concavity, so your final answer would have to be g is concave up. Concavity, we use parentheses. On the interval, -4 to 0, from 3 to 6. It has to be in parentheses to be considered for full points. I have no doubt that some of the work that we did up here would get us some points. I think this was worth 3 points. You'd probably earn 2, but you wouldn't earn the last point if you use brackets, because in the world of concavity, we use parentheses only. And my friends, that's it. That brings us to the conclusion of this video on functional analysis. This is, I would say, a guaranteed topic on the AP exam. I wish you guys all the best. I know at Southwest and East End, we've been counting down the days. There are 28 days between us and the May 9th, 2012 AP exam. Best of luck to everybody.